Displayed on screen is the relationship between stress and strain of pure nickel. Stress is measured in gigapascals, and strain has no units. In order to find the Young's modulus, we need to find the slope of the graph, which is displayed as 207 gigapascals. In order to find the yield point, we find where the graph begins to curve, which is around 0.3 gigapascals. In order to find tensile strength, we find the highest point on the graph, which is displayed to be 0.4 gigapascals. However, tensile strength is not measured in gigapascals, but megapascals. So we need to times the 0.4 gigapascals by 100 to convert it to megapascals, which would make it 400 megapascals. In order to find the percent elongation, you minus the final point on the graph, which is at 0.07, and subtract it by the initial, which is 0, divided by the initial, which is 0, and then you times it by 100. The zeros cancel out, meaning you get 0.07 times 100, or 7% elongation. The reduction of the area percentage is found by inversing that equation, whereas it's 0 minus 0.07 strain units, which will get you 50%, which also makes the ductility 50%. In order to find the resilience, of the nickel, you times the yield strength by the strain at the yield and times them both by 1/2. Toughness is found by finding the definite integral of the total energy the nickel can absorb, which in this case is the area under the curve, making it 0.02 strain units. The integral is defined between 0, which is the initial point, and the fracture point of 0.38. Shown above, the curve can be broken down into 4 subsections. The first section, the elastic region, starts at 0 and it ends at 0.2 gigapascals, or 0 to 0.002 strain units. The second subsection is the yield point, which is 0.3 gigapascals, or 0.007 strain units. The third region is the plastic deformation area, which starts at 0.35 gigapascals and ends at 0.40 gigapascals, or 0.015 to 0.05 strain units. And the final area is the fracture point, which is defined from 0.38 gigapascals and 0.07 in strain units. The change in length displayed on the graph is 0.07, 0.7, and the change in width is 0.3.
Strain versus stress graph of metal 1, magnesium. Here we have our graph of pure magnesium. We have the stress values in gigapascals on the y-axis, and we have the strain values on the x-axis. And we also have the values for the elastic region, the yield point, plastic deformation, and the fracture point. We also have the original length, original area, and the final area as well. Calculating Young's modulus for magnesium, this would be the slope of the linear portion of the graph. And on our graph, that would be the slope of this orange line. And for pure magnesium, that's around 0.135 divided by 0.003, which is 45 gigapascals. Calculating the yield point, this is the point where the elastic region ends and plastic deformation would begin. So for pure magnesium, that's the end of this orange line, where the graph becomes no longer linear. And for pure magnesium, that point is around 180 megapascals. Tensile strength, this is the maximum stress that a material can handle before it breaks. This is also the highest point on the graph. So looking at the graph of magnesium, the highest point is right around this green area here. And that point is around 165 megapascals for our value of tensile strength. ductility, we have the percent elongation and the percent reduction of area. For the percent elongation of magnesium, it's around 5%. For the percent reduction of area, we have the original area minus the final area divided by the original area. Multiply that by 100% and it's going to be around 13% for magnesium. Resilience and toughness. Resilience is going to be the area of the elastic region. Toughness is going to be the area of the plastic region. So looking at the graph, the area of the elastic region would be the area under this orange line. The area of the plastic region would be the area under the entire curve after the yield point. So for magnesium, the resilience is calculated by yield strength squared divided by 2 times Young's modulus of magnesium, which is around 180 squared divided by 2 times 45, which is about 360 joules per meter cubed. And for toughness of magnesium, that value is going to come right about to 40.94 joules per meter cubed, and the 1000 is simply just a conversion factor.
Magnesium alloy. Online, I found a stress strain curve of magnesium 95.34 Ni2, Y2.66. I have since then put all the points on to show the curve here. So starting off, to find elastic modulus, we take the part here, and we calculate the slope of that. Now, after I did the calculations, I got around 30 for the elastic modulus of this, being mainly magnesium. And that's just taking rise over run. For the yield strength part, well, first yield point. The yield point is right here. You can see that as it stops being elastic and becomes plastic. And so any deformation after this point here will be permanent. Yield strength is just like this point. You just go left, and you can find it's 85. That's a point. You just write that right there. 85. Tensile strength. Let's see. Tensile strength. Oh yeah, that's just the max point before it fractures. So we can just look at the final point right here. Comes to be around 175. We put that in. Ductility, percent EL and percent EL. I'm not going to do it for this material because, yeah. But if we were to take the material and stretch it, we could calculate it. Let me see what I write here. You stretch the material and you find the change in area for RA and you find the change in length for EL. Those are how you find those two. You look at the corresponding values and you calculate. I think my partners went more in depth into that. Resilience. So, actually, wait, before I continue, I got this curve, this thing. This helped me figure out, you can see, Young's modulus, yield strength. This is the tensile strength, fracture point, and it shows all that. But aside from that, you also got the resilience. So we could find resilience as the area under the curve while it's elastic. So, did I calculate that? I didn't calculate that, but that's how you would calculate it. You take the integration from 0 to the stress in regards to strain. And toughness is, you can see, is just the entire area under an entire curve until the fracture point. So that's all that. Now for question 7. So we have here a 1 milliliter specimen of both the metals. I did everything ahead of time, but I'll show that the area of our cylinder is going to be 2 pi RH times our 2RH plus 2 pi r squared. So I did all the math for that. We have a radius of 20 some meters, which is zero point 0.2 meters, and it's 1 meter. So the area comes to be around 1.5 meters uh, cubed. And then we have our force is 4 kilonewtons, which is just 4,000 newtons, so that we are good units. We take those two things to find stress. Stress is just where is it? Stress is force over area, so that comes to be around 2,666 Newton over meter squared. With this, we can use Hooke's law to find what the strain is. We take the elastic module of each. So for strain of nickel, using Hooke's law, we found it to be, let's see, the strain of nickel is 59.26. The strain does not have units, and the strain of magnesium, we found that to be 12.88. With strain, we can now find strain L, which is just, or yeah, strain of the big L beneath it, which is just the normal strain times the Poseidon's value. So for nickel, I found that to be around point oh. Oops, almost just solved that for you. For that Poseidon's ratio, I found it to be 0.18 meters. And for strain L of magnesium, I found it to be around 0.03. Now taking that with the another equation we have here, which is just find deformation using deformation equations. We take the EL times the length, which since our length is 1, so we can find that this is how much it would deform with that much force. For the width, we just multiply them both since the radius is 0.2 meters. It'd be 0.4 because radius 2 times radius is diameter. And we could find the change in width of nickel. That came to be around 0.07. And the change in width magnesium, that came around 0.01. So yeah, that is how you find something, and that is the end of our presentation. Yep.